we talk about we have different models of communication. Message passing, share memory, what are their trade-offs? Then we talk about naming of communication. When we say naming, we care about direct or indirect. Then we have some trade-offs. Don't worry about synchronization here, because chapter 6, we spend a whole chapter on synchronization. We can remove slide 26, 27, 28, because again, all these examples, for your information, not for the exam. Chapter 4, then follow up on process, then we move on to thread. So first thing is, we should understand why we have multi-thread programming. Because we have 4 reasons, 4 benefits of using multi-threaded programming. That's responsiveness, better results, economical, better use of multi-processor architecture. And second thing is we have different type of thread, important. Okay, user thread, kernel thread, what are difference? One is more expensive, one is easier to create. And then, because we have these 2 types of thread, then we have 4 different mappings, which equal to 4 different models. Okay, many to one, one to one, one to many to many, and then there's a 4th one, which is a hybrid. Okay, 4th one is a hybrid of combining one-to-one, coexist of one-to-one and many-to-many. So even in today's operating system, how shall we map user thread to kernel thread are still developing. People still doing research. In Android, different version of Android, we're still evolving on what will be a better mapping, what will be more efficient use of operating system. Then, semantic of fork and execute, not important. Okay, we practice in tutorial, we practice in project, then that's it. In the exam, we will not test on the syntax of fork, execute, write thread, or write any C code. Don't worry about signal handling at all. Okay. Thread pool, important, because in practice, in a lot of system admin job in corporates, one of the job is to set up this thread pool, because without thread pool, you either experience longer latency in creating thread on demand, or you may be exponentially increasing the total number of threads and then crash a server. So thread pool is important. What are the benefits of thread pool? Make sure you understand and make sure you remember for the future. Don't worry about pthread, Linux thread, Windows XP thread, Java thread, Android thread. All those are examples only, not for the exam. And then we move on to chapter 5. Okay, chapter 5 is on scheduling, one of many important chapters. So first, make sure you understand the reason behind we need CPU scheduling is for each process, we will have interleaving of CPU utilization and I/O. For those processes using I/O, we should let other processes to run so that we can make use of CPU time more efficiently. This is graphic illustration, alternating execution, context switching between different processes. Before we go into different scheduling algorithms, we talk about objectives. So make sure you understand what are the different criteria: CPU utilization, throughput, turnaround time, waiting time, response time. And then all different scheduling algorithms we go through. I hope we all understand by now there's first come, first serve, there's shortest job first, there are preemptive and non-preemptive of shortest job first. And then we talk about, well, don't worry about this exponential averaging. Okay? It's good to have as a knowledge, no need for the final exam. And then we talk about priority. So priority is another important scheduling algorithm. There's also preemptive and non-preemptive of priority. Round robin, another important scheduling. It's how do we set up the quantum of round robin is important, because if we set it too large, essentially this round robin become first come first serve. If we set it too small compared to the context switching time, then we'll be spending a lot of time switching context. That's overhead. Multi-level queue, well, it's important that multi-level queue is used in practice, but in our exam, I think I will keep it simple. Okay? I feel there's no need to go into the complexity of multi-level queue in our exam to make your life more miserable. So we'll keep it simple, okay? It's good to know that used in practice, that we mix different scheduling algorithms, but for the purpose of the exam, let's keep it simple. Again, remove all the operating system examples, okay? They are for your knowledge, not for the exam. That's chapter 5. And then, once we understand and we start schedule a lot of process concurrently, as we know, typical operating system have 50 or 100 process or threads running at the same time. Then one of the important things is to do synchronization. We first show if we do not synchronize, we could run into the problem of race condition. Make sure you understand why we have a race condition and how we can fix race condition. To fix race condition, we need to apply one of these critical section problem solutions. Before we fix critical section problem, we have 3 requirements: mutual exclusion, progress, and bounded weighting. So make sure we understand what are these 3 requirements, because they are important. Don't worry about Peterson solution. Remove this for the exam, because it's not really used today. But what really used is important: test and set and swap. So make sure you understand how we can use test and set and swap to solve critical section problem. And then, most importantly, we show that test and set and swap does not give us very easy encoding. So in practice, most operating systems use something called semaphore. Very, very important. Semaphore and mutex. Mutex is essentially a semaphore with 0 or 1 values. So how do we define semaphores? How we can even use test and set and swap to realize, to fulfill semaphores, to implement semaphores. So semaphore can even implement with either busy waiting or no busy waiting. What are the differences? And then we presented 3 classical problems of synchronization. extremely important because they are applied everywhere in today's software. So the first two problems are important. The third problem we will not include in the exam. Okay, I think that would be too much. Don't worry about Daniel Philosopher, even though it's also an important problem, but not for the exam. Not for the exam. Okay? First two problems are more important. Make sure you understand what are those problems, what are the solutions using either semaphores, mutex, or even more fundamental test and set or swap. And then, since we don't worry about Daniel Philosopher, we don't need to worry about monitors. Okay, remove monitors. Remove everything with specific operating system examples. Solaris, XP, Linux, pthread. They are good for your knowledge. No need for the exam. So that's chapter 6. And then build on. That's a good question. So to repeat the question, do we need to understand the code for test and set semaphores, or we need to only understand the concept? So the answer is, you do not need to write C or Java level of code to make it working. We definitely will not enter your code to run. But similar to a lot of solutions we provide in the slides, that at least you should be able to write this type of pseudocode, so that give you a question you need to be able to somehow solve with this level of pseudocode. So does that help your answer? Okay. So no need for C or real C++ or Java code, but for synchronization, you do need to have the ability of certain level of pseudocode. Okay. That's chapter 6. Synchronization is very important in modern operating system, because again, the key for modern operating system is to support many processes to run at the same time. Then to support many processes run at the same time, we definitely need synchronization. Different type of logs, different type of semaphores. Otherwise, we go back to the most fundamental early days of operating system, only support one application. Then with synchronization, we come to possibility of deadlock. That's another important chapter, because deadlock do happen. It's real. We need to do something, or at least if we don't do anything, at least we understand why sometimes our laptop freeze, why sometimes server crash or not crash, but it doesn't do anything. So first thing about deadlock is, when does deadlock take place? We need 4 conditions to hold at the same time. What are those 4 conditions? Make sure you understand. Otherwise, there's nothing to talk about for deadlock. So there are 3 different ways to handle deadlock. Make sure you understand. Even though the third is not really handling, it just ignore the problem, but if it happens, we reboot. For deadlock prevention, essentially we have one solution for each deadlock condition. And then more reasonable is to have a deadlock avoidance. We talk about safe state, we talk about how do we remain in a safe state. And most importantly, we present Banker's algorithm. Give you a set of current state. We all should be able to run Banker's algorithm to determine, are we in safe state are we not in safe state? If we given a request, we should all be able to use Becker's algorithm to tell, shall we or shall we not grant this request? If we grant this request, will we enter into a safe state or an unsafe state? That's deadlock avoidance. Don't worry about deadlock detection, okay? Just to make your life easier, or make our life easier. That's chapter 7. So next, we start going to memory. With memory, we first, so don't worry about all this dynamic loading, dynamic linking, swapping. The first important thing is contiguous allocation. There are different ways we can do contiguous allocation. Best fit, first fit, worst fit. Hopefully with project, we all practice in all these different dynamic allocation strategy. And then there are problems with all this allocation because we can have external fragmentation, internal. Questions? External fragmentation, internal fragmentation. So we can do compaction. What are compaction? What are the challenges if we apply compaction? Then, if we don't do compaction, then the choice leaves us to paging. Okay, paging is extremely important for memory because paging is used in almost every single modern operating system. So we have basic paging with page table, and then we have paging with TLB, translation lookup side buffer, so that we can look up the page table faster. Important concept to know. And then to evaluate paging with TLB, it's important to understand how do we evaluate that, because we use effective access time. Effective access time essentially is a weighted average of whether we have a TLB hit or we have a TLB miss. With page table increasing, we can organize paging in 3 different ways. Hierarchical paging with multiple level of page table, hashed page table, or inverted page table. Other than inverted page table, all the rest, we have 1 page table per process for each process. They have their own page table. With inverted page table, we have 1 huge table for all the process. Make sure you understand the benefit and drawback. Okay, the benefit in this case is now we only have 1 page table for all process. The drawback, one obvious drawback is now every process needs to access this page table. Read is fine, write we need to synchronize. So this is one of those classical problems of synchronization. Which one? This turns into a reader-writer problem. Every process can read on this table at the same time, but every time someone needs to write to this page, some process need to write to this page table, everyone else needs to wait. Very interesting problem. Segmentation is the other important concept because segmentation is used with paging in almost every single modern operating system. And then, again, don't worry about these specific examples. They show that paging is used with segmentation, and that's enough for you to know. That's chapter 8. And then we come to chapter 9. So chapter 9 tells us only paging is not enough because physical memory is never enough. We have 4 gig physical memory, 16 gig of physical memory. Today's servers usually have 200 gig, 500 gig of physical memory, but they are never enough. If we have 100 processes, each process have a 4 gig logical address space, we never have enough physical memory. Then we need virtual memory. With virtual memory, then we need to have something called demand paging. So how does it work? Very important. It works with something called page faults. So what are the steps of page faults? This is a regular system operation where compared to segmentation fault is an error condition that we need to stop the system and fix the error. One of the key steps of page fault is when we have no free frames, then we need to find a victim frame. How do we find a victim frame? We have many choices. Page replacement algorithm. So make sure you understand all the page replacement algorithms. Don't worry about LRU approximate algorithm. They are practical, they are used in practice, but for this course, we only care pure LRU. But for the exam, we only care about pure LRU. Okay, make sure you understand the key concepts. Okay, thrashing is an important concept. Don't worry about working set, okay, for the exam.
We have to write pseudocode.
Okay, the question is, do we need to have pseudocode for LRU? Well, okay, so let me repeat my previous statement. You will never need to write any C code or Java code or C++ code. Okay? So you will not need to understand or implement LRU approximate algorithm. Okay? Then the degree to understand LRU is if you're given a sequence of memory access, if you given the number of physical frames, you should be able to tell how many page faults you have. Okay? So don't worry about memory mapped files. Don't worry about other issues. Don't worry about programming structure. Don't worry about page cache. Okay, that's chapter 9. And then we come to chapter 10. So a few things important in this is what a file system. We say a file system includes a set of files, a directory structure, and for directory structure, we say we could have the most flexible directory structure is a graph. Then with a graph, we could have the challenge of running into cycles. So how do we avoid cycles? The other important thing is protection. So how do we determine what are the different protections? Make sure you understand. How do we modify them? Don't worry about Windows XP or Linux specific details. So not much for this chapter. And then we come to file system implementation. So the first important thing is we have different allocation methods, contiguous, linked, index. Again, every time we have multiple methods by operating system, make sure you understand how different option works. What are their trade-offs? What are benefits? What are drawbacks? So this is a theme throughout the semester. Then there's free space. How do we manage free space? Give you a disk, give you the size. Can you tell me how much is this free space management needs? Don't worry about page cache again, even though we all know, we all understand page cache is important, but not important for the final exam. Don't worry about all these examples. Those are used for your knowledge, not for the exam. Don't worry about NFS. Don't worry about Google File System. They are presented for your benefit, for your knowledge, not for the burden of final exam. Then we come to today's lecture. Let's see, where's chapter 12? So chapter 12, you make sure you understand what's the disk structure look like. How do we evaluate the access time? Then, the most important thing is, we know rotational latency, we cannot do much, then we can do something as operating system on seek time. Make sure you understand how different scheduling algorithms work for calculating the disk head movement, which is proportional to the seek time. And out of those algorithms, scan, C-scan, look, C-look, we need to know the direction. How do we know the direction? Make sure you look at the question. Usually the question not only give you the current location, but you will also be given the previous location. So if you are given the previous location, then you connect the dots, you know what the next direction should go to. Then don't worry about anything about swap or RAID. Okay. So that's the end of this semester. So for the final exam, it will be very similar to the midterm. You're given 2 hours, you will have 6 or 7 short questions, you will have 3 to 4 longer questions that take more time to work. Similar to any other exam, there will be questions that will be easy to answer, there will be questions that will be difficult to answer. You should start from those very easy questions. Answer those first. Spend more time on those difficult questions. Okay? Is there any questions? Yes?
Is the grading at the end of the whole course an absolute scale or is it relative to everyone else?
Okay, very good question. So the question is, at the end of the total grading, whether this is an absolute grading or this is a proportional, relative grading. So, as a requirement by the university, this course, I believe many other courses, we are given a percentage of how many A's, how many B's, how many C's, how many D's we will be given out to the whole class. Say we have 200 students, actually 204 students in this class. A and A minus, we are given 15% of this whole class. Okay? And then I think from B minus and up, we'll have half of the class that will be given B minus and up. So majority of the grades will be relative, but there's a but. For extremely good scores, extremely bad scores, there will be no relative. Say if there are 10 students all score less than 10 marks in the final exam, they will all be given F. Okay? So F and A plus, there's no relative. So if there's 10 or 20 students all score extremely well, they all be given A plus. If there are 50 students, they all score extremely bad, they will all be given F. So for extremely bad or extremely well, they will be absolute. Okay, depends on your grade. And the majority, the remaining, will be relative. No. So, like I said, if there are 10 students all score 100, then they're absolutely good. There's no argument. They all get A plus. Okay? But other than that, other than those extremely, if you look at it, you know there's no way you don't give an A plus to this student. So for those good, I mean, let's say top 15% of the whole class, then that will be definitely relative. So throughout the years, sometimes the A or A minus cutoff line is 75. Sometimes it's 80, sometimes it's 85. Then those definitely be floating. Okay. So that's, I think that applies to most other courses as well. It's not an absolute relative, it's not absolute fixed grading. Any other questions?